Okay, it is recording. So let us begin. All right. So evolutionary computing. We're going to continue what we did, what we were talking about yesterday. And so yesterday we stopped at the selection process, right? So this is the selection process where was what we talked about, right? Roulette wheel selection, tournament selection, and the different ways you select some potential solutions out of the populations that you are then going to um, perform various operations on, create offsprings out of, right? So we talked about like the roulette wheel selection, where based on the fitness function, um, the higher your fitness function, the better your chances are of getting selected as a parent. But that also means that even if your fitness function is very low, that is, even if you are basically the worst uh, solution in the entire population, you still have a chance of getting selected, right? So that is the essence of genetic algorithms or evolutionary computing. That no matter how bad you are, you still have a chance of producing the next generation, right? So now let's talk about the variation operators, right? Because we talked about the selection operators. Now we need to talk about the several types of variation operators and how do we separate between different types of variation? Okay, let me turn off the laser pointer. Okay, so um, the job of the variation operator, as we talked about yesterday, is to produce new potential solutions out of the pool of existing solutions, right? And they are usually divided into two different types based on how many solutions out of the population are you using, right? So if you're using just one solution and then you're manipulating something within that solution itself, some of the parameters of the solution, some of the values of the strings, then that is a mutation operator, right? Then that number of inputs is called arity, out of from the word parity, if you know that. So if arity is one, then it's a mutation operator. You're mutating a single sequence, right? And if your arity is greater than one, so if you are combining multiple solutions in some various ways, then they are called recombination operators. And specifically when arity is two, so when there are two solutions that you're combining, then arity is called crossover. And these terms come in from Darwin's theory of evolution, right? So they come in from genetics. So and crossover, mutation and crossover are by far the most common operators used, right? But that does not mean there are no other operators are possible. Arity greater than three, where more than two solutions are combined, there are effectively stochastic ways of doing this, right? So one of the ways where arity greater than two, so three or four uh, different solutions are combined, is for every single position in each solution, you add in, say, you have a 30% chance of picking from 33% chance of picking from solution one, 33 from solution two, and 34 from solution three. Right. So that is a very typical solution that is used for when you are combining three different inputs. Right. Now, initially, there were lots of research papers that said that like doing pure mutation is more likely to produce uh, uh, better solutions, right? Where a single and if you do crossover, then the odds of you improving the solution is the same as the odds of you uh, decreasing the quality of the solution. So that is why there was a lot of initial discussion, and I'm talking about in the 60s and 70s and 80s, where people would use just mutation, right? And they would not use any kind of recombination operators for the fear that your solution is no longer guaranteed to always improve. But there was a lot of math done behind the scenes, and it was generally proven that neither one is guaranteed to improve performance in the short term, but both of them correlated with improved performance over the macro scale, over the larger scale. So generally speaking, if you're using an evolutionary approach to solving a problem these days, you're probably going to be using both of them, right? You're going to be using both of them, or you're going to be randomly choosing between them, right? So and something else you should always keep aware of is that the genotype to phenotype conversion, right? So if you create something that has no analog, if you create a phenotype that has no analog in the genotype, that that might mean that you have come up with a solution that is not a valid solution, right? So that means it would mean that if you implement it, then it breaks the constraints of the original problem itself. So you have to put in those checks initially. So let's talk about the mutation operator first, because it is very simple, right? The mutation operator just causes a very small amount of variance, random variance, right? It takes in one solution, that is one genotype, and it delivers another genotype, right? And this randomness, this stochasticity, is what makes it an evolutionary approach, right? Um, and not a heuristic approach. So a heuristic approach would have rules, right? It would tell you that if your genes are combined in such ways, if you have 50% of A and 35% of T and 20% of G and so on, then your C has to be this particular percent. Like that would make it a heuristic operator. But mutation is purely random. So you have to make sure that your element of change, that whatever you change the solution with, is completely random. And for various different ways, there are various different representations available, right? So for binary genetic algorithms where your solutions were not ATGC or genes, they were like binary strings, right? So there'd be zeros and ones, right? And so in those cases, a single mutation, the change from a single mutation operator is not much. It's a very percentage-wise, it's a very small percentage change, but it is essential to introduce like diversity of solutions. Right? For finite state machines or for continuous variables, it works essentially as a search operator. So it tells you that, okay, um, changing an individual solution, does it still correspond to one of the states in the machine, right? And for genetic partitioning, it is hardly ever used, right? Um, Something else that is very good about the mutation operator is that, remember, these are discrete operations, right? So if you think about it, many of the solutions for larger problems are not discrete solutions; they are continuous solutions. So any changes in them would make them like they are differentiable and continuous solutions, right? So in case of discreteness, in case of the discrete phenotypes that we are dealing with, how do we know that are there any missing solutions, right? So if you have sets of solutions, if your original population, um, oops, if your original population has sets of solutions, then how do you know if you haven't missed a solution in between them? Right. That is somewhat think of the maze problems that I showed you yesterday, right? So how do you know that there is a maze problem that you haven't checked yet? Like there is a potential path that you haven't checked yet. But the mutation operator essentially makes sure that you're exploring all these in-between spaces between solutions, right? And so if you run mutation operators infinite times, you are going to convert essentially any solution space, any discrete solution space, into a continuous solution space. So that is the advantage of the mutation operator. And now, what does it look like practically? Well, let's say initially your genotype, your phenotype, um, your string of values was 1111 in binary, then what mutation does is that it changes one of these at random. So it goes from uh, 7 ones to 3-1-0 and again 3-1s. So this is the change of a mutation operator, and I'm gonna write it out in code, and you'll be able to see it more clearly, right? And when arity is greater than 1, then you get a recombination operator, right? And in our case, we are going to talk about the crossover operator, right? So in this case, you're not changing one solution, you're taking two solutions and you're merging them in some way, right? So, and which information, where you are, what information you are losing and what information you are keeping has to be stochastic. Right? If it is perfectly deterministic, then again you lose the power of genetic algorithms. Right? And this is the reason why people uh, like years back didn't want to use crossover operators, because in many cases the offspring that they were generating were worse, right, than the parents. And so people would knee jerk say that, like, um, if at any two steps you are seeing that the crossover operator is creating poor solutions, then how can it be that over a long enough time scale, a crossover operator might create better solutions, right? And they would be right that if you just do crossover, then there is no guarantee of you getting better solutions. But the thing is, uh, the way evolutionary computing works is that you're cutting off poor solutions, right? You're the core conceit of evolutionary computing is survival of the fittest. So even if you are creating poor solutions, both of those poor solutions would get cut off, right? And they would not, well, like the odds of them getting cut off are very high, right? They would not survive over generations. So that is why, even if like individually they sometimes crossover can sometimes cause poor solutions, on a long enough time scale, they're going to continue create really good solutions. And the hope, the why we do this is simple, right? Like people have been doing this over millennia, right? People do this still till now, right? By breeding different plants together to get different colored plants, different colored flowers, and tutor cats and more specialized dogs and so on and so forth, right? So this is a known approach to create better offspring over generations. So what does it look like in practice in a very simple example? So the same as this, the binary phenotype, the binary genetic algorithm phenotype. Let's take a couple of different strings like this, right? So your parents have been selected like this. So your parents are all 7 ones and 7 zeros, right? So what crossover does, or like recombination operator, I'm using both of them uh, uh, I'm just using both of them interchangeably, but they mean the same thing, is that you pick a random spot in both parents for the cut, right? And what you do is you take one part of one parent and the remaining part of the other parent, and you combine them together. And so now you have two different offsprings. And I'll show this to you when we are doing code, like how this actually works. And this is very simple. This is very obvious, right? It's not very complicated at all, right? This is how This is why it's called crossover. Right? So this is the crossover operation. So and that leads us back into once we have done this, and once we have done parent selection, survivor selection, we get back, we take these offsprings and we shove them back into the population. Right. So one part we haven't talked about till now is the initialization and the termination part. Right. So how do we start our genetic algorithm, and how do we know that we have reached the end of our genetic algorithm? So, and I have talked about this yesterday, right? So there are, um, you can imagine that in some cases when there is only one potential solution, where your fitness function essentially tells you how close you are to the actual correct solution, then in those cases the termination is very simple, right? But in most general genetic algorithms or evolutionary computing setups, there is no single termination setup. So how do you know how do you know when to stop, right? So the initialization is done at random, right? And we s- we spread it out. We spread the randomness out enough that we cover most of the solution space, right? All the way from edge cases to like existing solutions and so on and so forth, right? Uh, Something else that usually is done when you're doing genetic algorithms is that you run a genetic algorithm for say 500 generations, and you terminate it, and then you take the population that you have created from that genetic algorithm to seed the next step of the genetic algorithm. Right. So you take some of the uh, like good solutions, some of the poor solutions from once you have already done a genetic algorithm approach, and then you feed it into the next approach so that your starting population is in some way fitter. That's what. That's why a lot of so this is similar to when we talked yesterday, not yesterday, when we talked last week about randomized hill climbing with restart. So or neighborhood search with restart. So when you're searching a known space of solutions. And you have finished searching, you have not found the perfect solution, but you have found a location which seems to be full of good solutions, right? So the next time you start your search, you zoom into that location and you search in detail that location. So that is what a lot of genetic algorithm approaches do. But don't fill it up with the solutions from the previous one, because then what happens is that um, you miss the randomness factor, right? The big advantage of genetic algorithms is that even really terrible solutions can sometimes drag your entire population away from getting stuck in like local extremes. So don't completely fill up your population with an existing genetic algorithm output, but seed your population. Like some of the solutions are going to be this, right? And finally, how do we terminate? Well, uh, once we reach some fitness, that fitness can be 100% if you hit the correct solution. That is one way. We might hit a termination on the number of generations we allow, right? Like yesterday's uh, little assignment that you did where you had to run along, right? In those cases, I could have told you that like you allow only 500 generations. If after 500 generations you're still not able to hit 200 meters in distance, then we need to change up the starting parameters, right? It might also be that we reach some minimum level of unique solutions, right? The diversity increases to some level where we are comfortable that, okay, we have explored the entire solution space and we have some really good potential solutions that we can explore later. Right? So that is one way of stopping. And finally, this is very similar to if you have done neural networks or if you've heard of neural networks, early stopping, right? So where you have not hit the generation limit, but as the number of generations is going on, the fitness is no longer improving significantly, right? So your fitness may have peaked at like 70%, 80%, and it has plateaued, right? So uh, this could happen due to many different conditions, but generally speaking, continuing to explore is like throwing good money after bad. So you generally speaking, you stop. So now we have covered essentially the entire structure of evolutionary algorithms, like the entire architecture of evolutionary algorithms. You should know um, when you're applying EA or GCs to a problem, um, there are various different types of evolutionary algorithms, right? So the most common are binary strings, right? And real valued vectors. Binary strings and real valued vectors are very similar in some ways. Binary strings just have 0 and 1, and real valued vectors can have more than 0 and 1, but they're stored in similar ways, right? Um, Finite, if you are training using finite state machines, then you are doing evolutionary programming. And evolutionary programming is a very widely used approach to create mathematical proofs. Before deep learning came along and before modern transformer architecture deep learning came along, evolutionary programming (EP) was considered one of the really, really good methods of coming up with mathematical proofs of very challenging problems, right? Where brute force is impossible, almost impossible, but humans were stuck. And finally, Lisp trees or regular expressions can also be used for genetic programming. But this is Lisp trees overall has fallen out of fashion. So, I mean, if you're still interested in genetic programming, there are still different approaches that people are still using, but overall they're no longer widely used, right? So in most cases, in the real world, if you come across genetic algorithm approach, say to LLMs on the outer shells of LLMs, you'll find that they're usually using real valued vectors for picking of parameter selection processes or PSOs, particle swarm optimization, or they're using finite state machines to do evolutionary programming to solve mathematical proofs, right? Those are still doable. So, and you should understand that the selection operators, obviously, they only use the fitness function, right? Remember, the selection operators can be roulette wheel selection, tournament selection. The selection operator doesn't really care about the parent selection operator doesn't really care how you're representing the parents, how you exactly you're representing all the possible solutions, right? So that is not the job of the selection operators. So they're independent of how exactly you're representing the base level data. All they care about is how close is each solution to the perfect solution. So let's look at one example of how to use genetic algorithms for a problem. And after we have gone through this example, I'm going to switch over to Python and then write out a code for genetic algorithms, like a very basic, very simple code for genetic algorithms step by step, so that you can follow along and we'll apply it to a different type of problem, right? So that you have some experience with two different types of problems to apply genetic algorithms, right? So the first problem we're going to use is we are going to go back to the original toy problems, right? So I talked about the three important toy problems for artificial intelligent agents. Well, the three problems are the 8-block puzzle, the n queens problem, and vacuum world, right? So out of those problems, the n queens problem is really good for showing how uh, genetic algorithms can be applied in non-intuitive ways, right? So this is the n queens problem, right? So if you have placed a queen here, then you cannot place another queen in any of the blue squares, right? So that is the n queens problems, and we have talked about this enough that you know. Right? So how do you want to represent this as a genetic algorithm problem, right? Like this is the phenotype, right? This board and all the queens. So how do you map this to a genotype? Any any ideas? It's not very complicated. There are a few ways, but there is one very simple, very obvious way of representing this as a like combining all the queens that you would place into one array, like an array of numbers. How would you do this? Just take a guess, or write it out in chat if you want. How would you combine this? Um, well, a matrix is fine, but this can be seen as a matrix, but you want to make it simpler. Yes, the coordinates of the queen's position, but how do you do it if you're doing it as a one-dimensional array, right? Just as a simple array. I mean, you're on the right track. I mean, both of you have given the correct answer, essentially. I mean, okay, so let's move on. Like you have given the correct answer. So one of the simpler ways of doing this is like Eric and like Dylan said, well, not x comma x comma y, because again, that makes it slightly more complicated. But you can make it even easier, right? You can just write it out as numbers. So you're in position in in column one, you're in position one. So you're in row one. So the location, yeah, yeah, Alan and Eric are in the right ballpark, right? So uh, you just have a little more information. So like you see the 1 1, the 2 5, the 1, the 2, then the 3, those are not necessary, right? Those can be inherent. So if you store it as like this, like as I show here, then just the location, the position of all of these tells you which column it is, right? So if you're in position one, you're in column one. And if the value stored is one, then you're in row one, row three, row five, right? Row two. Yes, you're using the index as the x coordinate, right? Yeah. What this has done is that all possible phenotypes have a representation in the genotype, and you have made this much simpler. And this is something that you can very easily use genetic algorithm on, right? Because you can see that this is you can very easily do, yeah, yeah, exactly, yeah, yeah. Alan is right and Eric is right, yeah. And so after this, you apply your fitness function, right, to check. Yeah. Since two queens in the same column is not a valid solution, you can never have more than one value in one position. So you have reduced the solution to something that is more usable. So how do you evaluate the fitness of this, right? So the fitness is essentially how many queens are you able to check at any time, right? The and then the total penalty of the whole board is the sum of all the penalties of all the queens, right? And the job of the evolutionary computing approach is to minimize this penalty, right? And so the fitness, that is the fitness function, is the minimizer of the penalty. So you're trying to maximize one over penalty, one over sum of all the penalties, right? So the penalty of an individual queen would be that how many queens are in the blue squares, right? And then you do this for all the possible queens, and this is like numerically calculable, right? You can use you can use a little bit of algebra to basically calculate how many queens from this, how many queens are falling into your column, right? In here you can see like for this queen uh, you have a penalty, right? You have two penalties, two queens are falling into you, right? So uh, and you can continue to do this, and you can calculate the possible penalty for each queen, and then you sum them up to find the sum of all penalties. And then the goal of the fitness function would be maximizing one over sum of p. That would be the fitness evolution. So mutation is very simple, right? The only small difference is that you don't want to change one value, but you want to swap position of two different values, right? If you change one value, then if you say, for example, here, if you just change 4, and if you change, if you just change 5 over here, if you just change 5 over here and we change it to 6, then it is immediately an impossible genotype, right? You immediately 6 and 6 means that it fails. So what you want to do is you want to swap. You want to swap between 3 and 8, or you want to swap between 5 and 4. So that would be the mutation operation in this case. So what this means is that the mutation operation is always different in different types of solutions. The only thing that is common between any different solution approach and the mutation operator for that is that are you able to do it on only one solution, right? That as long as that is true, then as long as your arity is one, what you have is a mutation operator. Right? Now, the recombination operator, the crossover operation, is slightly difficult here, right? So just make sure that when you are doing this crossover, right, what you have to be careful about is there are no repeats, right? So what you do is you choose a random, so you take two solutions like this, 135, 26, 4, 7, 8, 135, 26, 4, 7, 8, and another solution, 8, 7, 6, 5, 4, 3, 2, 1. Right. So you take this solution and you take this solution, and then you create this. You create the second part um, by first skipping over all the solutions that what like skipping over 135 from yellow. So you already have 135 here, right? So you start from here. So 5 is already in 135, so you don't pick it. 4 is not in 135, so you pick 4. 3 is in 135, so you skip 3. 2 is not in 135, so you skip you keep 2. 1 is in 135, so you skip 1. And the rest are 876. The rest are the values here. So you have 42876. And you do the same for the second part. So you start off with 876. 2 is not in 876, so 2 comes in. 6 is in 876, so 6 doesn't go in. 4 is not in 876, so 4 goes in. And then 7 and 8 are both in 876, so none of them go in. So the rest is 135. All the remaining values go in. Right. So this is how the recombination works. I mean, it's obviously not very complicated. And if you're doing it in Python or in C, this is much simpler, right? In C, you're just if the values are you're just checking for individual values, and if they still exist, then you place them. And if they don't exist, then you don't place them. This is very simple. But you have to understand, you have to intuitively know what you're doing, because if I give you this in an exam, you should be able to understand what you need to do this particular combination. Um, did you follow along, right? Or should I explain this one more time? If you
Professor,
if you
play,
yeah, sorry, go ahead.
yes, can you play it one more time, Professor?
Sure, yeah. So in this case, what you're doing is what's called the crossover operation, right? So you have two solutions, the blue solution and the yellow solution. You want to combine them in some such a way that some part of the blue solution mixes with some part of the yellow solution, and vice versa, right? So the way you do this, first you pick a point in both solutions for cutting it, right? It can be after 3 positions, it can be after 5 positions, it doesn't matter, right? So you pick some point to cut them off, right? So then you take the first part of the first solution remains constant, right? And then you take the blue solution is here, it's constant. Now you want to mix the blue solution with the yellow solution. So you start with the values in the yellow solution. So the first value in the yellow solution is 5. 5 is already here, so you skip it. Then you get 4. 4 is not in 135, so 4 is pushed into the stack. Then 3 is in 135, so 3 is skipped. 2 is not in 135, so 2 is again pushed into the stack. Right, and then 1 is not 1 is in 135, so 1 is skipped, and then 8, 7, and 6, the original values are pushed into the stack. Right, and you do the exact same thing on for the yellow, right, as well. So you start off with 876, which is 876 you see right here, and then you want to combine this with this, the blue section, right? So the first value in the blue section is 2, which is not in 876, so it gets inserted. 6 is within 876, so 6 gets skipped. 4 is not in 876, so 4 gets entered, and then the rest are already in 876, so the rest of the value you want to enter are 1, 3, and 5. So 1, 3, 5. That is at, and now you have two different solutions from the parent solution. So your two parent solutions were 1352647 8 and 8765431, and now you have two new solutions, which is 1354286 and 8762415. So you want to check the fitness of this solution and this solution, and then decide which you want to keep and which you want to drop. Right. Did that help?
Yes, sir, it did. Thank you,
All
Professor.
right. All right. Thank you. Right. So now, once you have done this, turn off the laser point. So once you have done this, now you want to do selection, right? So, um, I mean, this is one suggestion for the selection, but you don't have to use this, right? You can use whatever selection process you think is good, right? So for the parent selection, so which of the parents are you going to send to recombine to do this crossover operation? Generally speaking, you pick any five possible solutions randomly, and then you calculate their fitness, and then you take the best two out of them to undergo crossover, right? So that's what you do. And then then the next part is the survivor selection. So which of these newly created offsprings get inserted back into the population, right? So generally, how you do this is you replace them, right? So you have your entire population of solutions, you sort them by fitness, right? And then anytime, and then you check the fitness of the newly created population. So you check the fitness of all of these and these. So all the mutated operators, the crossover operators, the recombination of all the new solutions that you have created, you check their fitness, right? And you check the fitness of all the solutions in the in your list of solutions of all the solutions. And then the first solution that you hit in your original population, which has a fitness worse than these solutions, you replace that with these solutions. Right. So what this means is that your remaining population's fitness has grown slightly, right? But this is somewhat deterministic, right? What you can do is I mean, another approach to this is based on how good your fitness is and how poor your fitness is. That is the chance of you getting replaced by someone with a better fitness value. So that is another approach. But there can be multiple different approaches, and all of them, none of them are bad approaches. So you can use any of them. Right? So this is a summary of all the things we talked about, right? Like the representation was the permutation approach. The recombination approach was called cut and cross fill. The probability of recombination is obviously 100%. If you're picked to, they always recombine. The mutation is swap. Right. And I talked about why it has to be swap and not just change one value, because it is, if you change one value, then it is going to be another value that is already in the list, and the solution is going to fail. Right. So you do a swap, then the odds of a mutation happening, I picked as 80%. It is up to you to what to pick. And the parent selection is the best two out of random five, right? So you pick five solutions at random out of your out of all the possible solutions here. And then you choose two who are really good to then recombine and mutate, right? Your survival selection is replace the worst solution that is worse than the offsprings that you have created. Your population size can be anything. In my test, it was random. Like this is supposed to be a homework assignment, right? So that is why I have this as a summary. But we are not doing homeworks for this class. So this is just an expectation of how you could formulate this problem. And you have two offsprings. Your initialization is random, and your termination condition is either you hit a solution or you run for 10,000 generations, and you stop after 10,000 generations. So, and pick the best possible solutions, right? And obviously, this is the one that I picked, but you can pick something different other than this, and you can come up with better or worse solutions. right? So this is essentially a full coverage of evolutionary computing. I mean, you can obviously go into a lot more detail, but let's see a few things about on a meta level, right? So what does evolutionary approach to finding a solution look like when you're looking at all the window of all possible solutions, right? So generally speaking, when you are solving an evolutionary approach and your population is truly random, well, quasi-random. If it is truly random, then this bottom solution is also truly random, right? Like there is no such thing as truly random. Truly random does produce clumps. So quasi-random populations of distribution is called quasi-random because most solutions are equidistant from each other. We want to cover the entire field, so most of our solutions should be equidistant from each other. So that is what that early stage of solutions look like, right? And as the evolutionary approach is proceeding, you will find that because of how we drop poorly performing solutions, right? Like the low fitness solutions are slowly removed from the entire population. As the population progresses, you will see that solutions that are very low on the pole start dying off. Right? Those solutions keep getting removed, and eventually, as we reach the late stage after like 500 generations, the only surviving populations are all high fitness populations. Right? So this is what it looks like, and so there's you should be able to notice something from this. Like this is very similar to when we were doing neighborhood search, right? When we were doing randomized hill climbing or when we were doing general neighborhood search. So this is kind of similar. And as I talked about before, evolutionary computing is a form of neighborhood search, right? So we talked about how many of the heuristics are require you to come to a good enough solution and then spend some time exploring the neighborhood of a good enough solution to find an even better solution. Right? But generally, we saw this problem that doing this kind of like neighborhood search or randomized hill climbing with restart, you tend to get stuck on local optima, right? You tend to get stuck on local dips or local peaks instead of exploring the entire solution space. Evolutionary algorithms, because of how stochastic they are, and because how they start out by searching the entire solution space, and there is very little bias, right? Your evolutionary computing setup is like rewards going away from the existing solutions, especially when you're doing a lot of variation checking, right? If you are doing a lot of recombination checkings, then you do get to search a lot more of the solution space, right? And that makes evolutionary algorithms very good, right? So what does a neighborhood evolutionary computing approach look like? Well, it looks like this. Wait, what happened? Oh no, this was supposed to be a video where you could see all the dots migrating up into the peaks as the evolutionary algorithm proceeds in the future. Huh. For some reason, this is now a still image. My bad. I must have changed something when I was correcting the slides. But you can kind of see what we're telling you, right? That all these dots are your agents, right? Your potential solutions, right? And this yellow field with all these peaks on them is the actual solution space of the function, right? So you start out everywhere, right? You start out with solutions in all over this space. But as it proceeds, you will see that these solutions, like all the solutions, let me zoom in. So all the solutions in the, okay. Oh, so I can't use the laser pointer when I'm zoomed in. That's kind of weird. So all these solutions are going to lose, are going to get cut off. And eventually all the solutions you are going to see that are going to migrate higher and higher and higher and find these peaks. Right. So that is how evolutionary computing approaches work. Yeah. Sorry, this was supposed to be a video. Right. So I will show you this, right? As an evolutionary computing approach proceeds over time, the best possible value increases very fast, and then it slowly plateaus, right? And this is only possible if there is no single good answer. If there is one good answer, then it's going to rise like this, and it's going to hit a good answer somewhere over here, and it's going to stop. But if there is no perfect answer, it's going to eventually hit a plateau, right? It's going to hit what some of these peaks, and the solutions are going to cluster on those peaks. So that's what it generally looks like. So generally speaking, when you are doing a lot of runs, when you're doing a lot of evolutionary computing runs, what you want to do is take your population from here to somewhere over here, right? And then stop, because the amount of time taken from to go from this go from this location to this location is about the same time taken to go from this location to this location, right? And the improvement here is very marginal, right? The improvement here is very small compared to the improvement here. So you want to spend most of your time here. You want to spend most of your time in this location, this part of your research instead of this part of your research, right? Like when I was doing my PhD, my initial PhD year, so like when I was in my second year of my PhD or my third year of my PhD, it was very interesting because I was in this part of my research where I was like finding interesting things about the stuff that I was doing. I was talking to scientists from all over, and like I was talking to scientists from NASA, I was talking to scientists from Microsoft, and we were progressing very fast. But the last year and a half of my PhD, I barely improved my solution, right? So this is the boring part, and you don't want to spend the majority of your search period on this boring part, right? So what you what always happens in case of evolutionary algorithms is that you run your evolutionary algorithm as soon as you see that you've hit a plateau of some kind where the increase is very slow and marginal, and you might even sometimes get small decreases. You stop, and then you start another run of evolutionary computing. And that is essentially how you solve a problem using evolutionary computing, essentially. Like keep stopping early, where your progress in this first half is very fast, these short runs, and then you keep doing these runs over and over and over again. Right? But is it worth expanding all of your effort on this, right? Like if you have reached something like this and you have a smart population, is it worth it to do another run where you start with this smart population with some different parameters? Well, it's up to you, right? And there are means and methods of doing this. Like I said, this kind of hybridization techniques, what they ask you to do is, even if you are starting, even if you have increased your population fitness to some level, and then you are starting another run with the population here, is that you don't take the entire population. You don't take the entire population of this place. You seed your population. You hybridize your old population with this new highly fit population, and then you run genetic algorithms on it, right? Which is that you will see that on average is going to give you better results. It's going to avoid getting you stuck in poor solution spaces, right? Um, modern use cases, evolutionary algorithms, like I said, uh, died for a few years, right? And it keeps happening. Every few years, you're going to see a bunch of papers coming out saying that deep learning or stochastic learning or some form of statistical learning has made evolutionary algorithms completely obsolete and they're never going to be used again. But again, a few years later, you're going to see that, like, no, no, people have found some solution where some set of problems where evolutionary algorithms are better than the average generic search algorithms. Right. Now, what evolutionary algorithms do well is that they would provide, no matter what kind of search problem you're using it for, they would provide you a very good baseline. And that is sometimes very well needed, right? Just in case of search problems, breadth first search is going to give you a very good baseline. Like you shouldn't, your search process shouldn't perform any worse than breadth first search. Similarly, whatever steps, whatever technique you're using, whatever intelligent agents you have designed to solve your particular problem, they should not perform worse than a more general evolutionary algorithm approach. Right? If they're performing worse than the EA approach, then that means your approach, your solution that you've come up with is not good enough. Right? And this is generally how people depict it. So there is the random search methods, depth first search, breadth first search, etc., etc. And then there are very highly specialized problem search methods, right? And these are methods like deep learning methods, which, if you fine tune on a problem, are going to give you more than human solutions. But the advantage of evolutionary algorithms is that they're going to provide you a better baseline than random search approaches. Right? On completely random problems, on zero shot problems, you will still find that EA approaches give you better solutions than zero shot deep learning methods. Right? Non fine tuned deep learning methods are still worse than EA approaches. But again, there are disadvantages of EA approaches because they are very slow, and because they are so generic, they're very tough to specialize. They require very specific problem formulation. So many problems, many different types of problems are very, very difficult to formulate as an evolutionary algorithm approach. So that makes it, again, very challenging. So uh, you are probably, if you are going to industry, you will find that evolutionary algorithm approaches are placed on top of specific DL methods or specific control theory methods, right? Where you hit a broad class of solutions, and you don't want to do Markov search, right? You don't want to do completely random search, so you tack in some form of evolutionary algorithm to find the most optimal parameters for a larger, stronger model, essentially. And like I said, her EAs keep coming up and dying and then coming back up. Right? And um, it performs well, and it is useful in modern research. uh, when you are submitting a query to a large language model, and you want to find out, okay, which type of query or which format of query performs best for the large language model, people have been using evolutionary approaches to see this, to search through all the possible contexts that you can give a deep learning method or a large language model, and to find out, okay, which cluster or which type of context given to a LLM allows LLM to perform best. So, and that is something that people are still using. Right? And like I showed you, there are certain specific approaches where EA is still pretty. All right, so this is pretty much the it for evolutionary computing. So what I want to do is I want to write out an entire problem, right, in an evolutionary computing setup. So let's do Jupyter Lab, and let's write an entire problem in okay, come here. Let's zoom in. Okay, so this is completely new. Let's see, new notebook, and let's call it genetic algorithm demo. Right. Okay. So is this, let me pull up Teams. Is this visible? Right. Let me full screen it. Right, full screen it. Okay. This is legible and visible, right? Okay. So let's start. So what is the problem that we want to tackle using a genetic algorithm? Well, the easy problem is the binary kernel, right? So let's say we have a problem that has given us a bunch of a string, essentially. So you have reduced the problem, like in the n-queens problem, into essentially a string or a vector, right? And the solution is a known vector, that your vector should have particular qualities, and the solution is that known vector, right? So in our case, let's say that let's skip the population genotype to phenotype conversion, because again that is very problem specific, right? Let's focus on the genetic algorithm part. So you have been given a string or a population of strings, and you want that string to match something. So that is an easy approach, right? So what do you need for a genetic algorithm approach? Well, you need random. So the first thing you need to do is import random, and then set a random C, right? So take a completely random value that has no meaning, right? And then you run. Okay. So let's say the target that we want to hit. Um, Let me check chat in case someone has any questions or anything. You're all able to see this clearly? Like this is readable? Do you want me to zoom in a little bit so that you can see the text?
It's good.
All right, thank you. Okay. So, okay, let's put this here. Okay, so the target, let's say, is the target that you want to hit, right? So this is the goal, is, I don't know, University of Houston. So this is your target, right? And then what is your genotype? Like what is your population? Well, it is all random characters of this length, right? So all possible ASCII characters of this length. So this is not binary, right? In binary, you'd have only zeros and ones. So this is a larger target space. So let's say your genotype or genes, say, is how do I do this? Uh, is a all possible strings, right? So okay, let's import string. So that would make this so much easier. So genes would be string dot uh, uppercase ASCII. That is uppercase underscore, no, ASCII underscore uppercase. I think that's it. Um, Plus obviously space. You want the space. I think this should work. Okay. Man, I forgot all the shortcuts. What is the shortcut for Control plus to add new add cell below? I think it's Control plus. It's Control B. Okay. So, well, the first thing we want to do is we want to encode the candidate solution, right? The chromosomes. Right? So that means all possible random individuals with a length of target. Right. So we want to create the candidate solutions. Right. So how do we do this? Well, let's create a function called candidate solutions, random solutions. No, uh, individuals. So random individual. Right. So all this is going to do is it's going to create a set of uh, completely random values like this that of this length, right? So you return. How do I do this? Okay, so dot join. So you want to randomly choose. So it's random dot choice from genotype, no genes. I think this is the correct structure for in range. what the length of target. So len target. Close, close, close. I think that did it. Okay. So let's see what those individuals look like, right? So for I in range uh, 10, that's it. So print candidate solutions are what are the solutions that we have created? So random individual. So we run random individual 10 times, and what are the solutions that we're getting? So let's run this. So these are the random. This is essentially your population. Right. So as you can see, these are completely random characters, uppercase characters with an occasional space in between them. Right. So this is what you're going to use for your population. Right. So then what is the next step? Well, before going into selection, well, we have to determine how do we check the fitness. Right. So the checking the fitness in this case is you can make it much more complicated than it is, right? So generally speaking, because we have like an actual solution here, like target equals University of Houston is like the one solution that we are trying to hit. Our fitness function here is very simple, right? We want to check whether each of the characters that we have created here, like is this character part of University of Houston? That is what we want to check. Right. But generally speaking, you don't have a single target solution, right? Your fitness function is not going to rely on a target solution. It is going to have to evaluate everything on its own merit, right? But in our case, we have created something simple. So let's just create a very simple fitness function where we send in an individual. And so what does it do? It checks whether each of the characters in the individual, um, each character in each location, is it the same character as the same location in target, right? And if it is, um, uh, give it one, and if it is not, give it say -1 or zero, right? So you add up how many characters are the same, and that's it, right? So you return a sum of something, right? Okay, so the sum is going to be somewhat complicated. So it should be one. It should be one um, when they're equal, right? So okay, this would have been slightly easier to do in C++, but okay, no, this is no. This is very easy to do in Python. What am I saying? For this reason, for this kind of comparison, the zip function exists, right? You may have, if I hope you have all done programming, 2000 level program where they teach you Python, so you know the zip function. So the zip function combines two different essentially two different values in one set, right? So what you want is you want to take the first character, like all of the characters in individual and in target, right? So you want to take in a for loop, for example, you want to take uh, uh, target 0 and candidate 0, right? And you want to compare them. So uh, so you want to take two characters. So it should be zip individual target. Um, no, one. It's going to be sorry. This is live coding is somewhat more challenging. So one for x comma y in zip, right? So that's how you do it. Um, and it is one if they're equal. and 0 if they're not, right? So if x equals, and these are individual characters, so you don't have to do dot equals, you can just do double equals. So you can do x equals y. Right. I think this is going to work. So one for xy in zip individual target if x. Okay, I think this is going to work, unless I messed up the format somehow. So let's check whether this is working or not before going into anything detailed. So for I in range, let's say, let's not do 10, let's do 5. I in range 5, let's create a random individual, right? So let's take uh, rand. No, don't do rand because let's do independent. Is equals to random individual, right? Now you want to print. Uh, this is some. Let's do f strings because we want to combine both of them, right? So you want to print independent. So you want to print independent. Uh, 15, I think. Yeah. Uh, uh, fitness equals. Well, I want to print both the independent and the target. So the fitness is the fitness of the independent value. So you calculate fitness of dependent uh, divided by the length of target. So how many? Uh, I think this does it. Let me see. Yeah. Okay. Yeah. This is fine. Right. So target length is 21, right? I didn't count it wrong. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 19, 20, 21. Okay, no, this is correct. Right. So you can see here, all of these have fitness 0 because none of them are common. But this has fitness 1 because one of the letters in here is in the UNIVRSITY of this F is in the correct position. Right. And okay, let's not do 15. Why did I do 15 instead of 21? Let's do 21. In this case, there are two different characters correct. So as you can see, this is working, right? The fitness function is. I think this is working. It's very hard to tell if one of these if the fitness function is wrong. Uh, no, it is very easy to tell whether a fitness function is wrong simply by running fitness of target. Yeah, the fitness of the target is 21. So it is correct. Okay. I don't know why I did all of this complicated stuff. So the next step after this is that we know how to calculate the fitness of an individual, and we know how random individuals are created. So if you go back to this and you go back to this, so we know how the initialization needs to be done, and we have the fitness function. So let's create the population. So let us create the population. Right. So the population is going to be very simple. Uh, uh, Create underscore population of a given size. And we just do this size number of times, right? So you return a list, right? You return a list. And we always do this inline, right? Let's not create a variable and then return that. So we create a list of random individuals. Is that what we called it? Yeah, we called it random individual. So we create a list of random individuals for X in range size. So that's very easy, right? And again, let's take a look if we did this correctly. So let's say we create a population of size 10, not 1, 10, and then print that out, right? So for independent individuals in population, print again F. Let's do an F string. The same. It was 21 long, so independent are uh, up to 15. No, sorry, up to. Why did I keep thinking 15? 21. Fitness equals to uh, fitness of the independence. Okay, I think this is correct. Right. And then let's print what is the best out of all of them, right? So max of uh, population, and you check this by the function fitness. So you should know this max function, right? That you're finding out the maximum value in this list, and the metric that you're using to calculate this maximum value is the function fitness. And then you print this out, right? So print again uh, f strings. That's always two f strings. So best individual out of the population is best, and then fitness of fitness uh, best. Doing the calc. Okay, there are too many brackets here. Is that it? Is it? Oh no, I need one more bracket. Okay, I messed something up. Huh? Did I make a mistake? It should be iterable.
There's a misspell on the fitness at the end of the line.
You mean
In your
After
print
the
statement,
best.
it says
Says
in your-
fightness.
yeah, it says fightness on your last line.
oh, okay. That shouldn't be the problem, right? Because that's just text. The error is it says that this is not iterable.
Yes, sir. I think it's partially recalling the fitness, but it's the yeah.
And the funny thing is we already calculated fitness here, right?
Yes.
Yeah, this worked, and then this worked. Population creation worked. This very strange error. For independence in population, fitness is the fitness of the individual. Okay, let's comment this out to see if there is still this. Okay. That is very strange. Because this is definitely iterable. I don't see any reason why this the fitness of individuals should not be iterable. For x equals okay, let me see. Fitness is of an individual is sum one for xy in zip individual target if x equals. No, this function is perfect. This works. And we can see this here. The fitness of our target is one. This works. Population creation works. So if I comment this out, does it work now? Following dependence in population. Let's do this. Fitness is fitness of individuals. Okay, sort of. Am I reusing something? This is such a strange error. Live coding. This just worked here. Okay. Hang on. This out. Let's just do print I, just in case something is messed up with the individuals. Oh, oh, this is returning. Oh, oh my God, this is such a silly error. I didn't put brackets here. Okay, so this was returning functions. Okay, I am so, ah, see, these are the joys of live coding that you would never notice, because you'd always forget. Um, so yeah, what was I doing? So fitness. Oh, let's just put in the actual values, right? So it's in IND, right? That's what I call it. No, I. So it's I summation mark R. Hold on. Very good. And suppose. Yeah. Okay. So yeah. So you can see that out of this generation of 10 values, the best individual we have is this. I hope you have some time. Yeah, we have time. We'll finish in another 15 minutes. So the fitness of this is 2 because there are two. Well, I don't know. UNIVERSITYOL. Yes. Oh, University of Houston. So I think a couple of these letters are common. So this is working, right? So we are able to create population. Right? So next up is the selection process, right? Let's going back to this, we have created a population. Next step is the parent selection process, and let's for our selection process, let's do something very simple. We want to get this over with fast, so let's do um, relay tool selection, tournament selection. Tournament selection is much faster, so let's do tournament selection. With a given population, and let's do tournaments of 3. Why not? We can change it. We can change it later, right? So in a tournament selection, you understand, right? What tournament selection is. You take all the you take randomly k number of um, uh, solutions from the population, and then you pick whoever is the best out of them, which is what we did, right? So the contestants for the tournament selection is you sample k number of times out of the population, right? And then you pick the best out of them. So, well, we don't even need to do this. We don't need to do contestants equals. Let's do it in one line. Let's make it simple for us. So the max of um, a random sample of the population of 3 value of k number of random samples, and the max we find the max using the key equals fitness. I think this is going to work. Random you sample population k times, and then you find the max of all those contestants using fitness as the function, right? Let's see if it worked, right? So again, let's create a new set of population of 10 values, 10 individuals. Then let's print the population. Let's copy and paste this. So let's print the population, and then let's print so population tournament with 3 contestants, right? If you spot me making an error, let me know immediately, because I don't want to spend too long on this. So for I in range, well, I'm saying 3 contestants, but it can be anything. But let's do 3 at the start, right? Let's not make it too much complicated for us. So the winner of a tournament selection section of the population that did we create the population? Yes, we created the population with k equals 3 again, and then let's print the winner. So, let's do tournament I plus 1 because it's going to start from 0. So winner would be winner, and then their fitness is fitness of the winner. One more bracket, then quotations, and then one more bracket. Yes. Okay. And population tournament with 3 contestants, and these are our 3 winners. So we are going to use, we ran the tournament 3 times. So these are the ones we would use for our selection. Right. So next up is the variation. Right. So we have done selection. Next up, we do crossover. Right. So let's write out how we're going to do the crossover part. Crossover is very simple, right? So crossover, you have parents, parent 1, parent 2, point to a child, you have random dot rand int. I mean the cutoff point, right? Uh, so this has to be the length of the target or of each. Either of the parents have the same length, so that shouldn't be a problem. So it should be between 1 and 1 before the end. So it should be the length of. So what I'm talking about here is this part, right? Where am I cutting it? So what is the point? So let me call it cut instead of point, because that will make it easier. So the cut is at parent 1, and it should be 1 before. So because you cannot cut at the end, right? So it has to be at least 1 before. It has to start here and it has to end here, right? So it's to be -1. So and then the combination is very simple, because this is not like the n queens problem, right? In the n queens problem, this part is going to be is usually slightly more complicated. Right? So this is very simple. So using simple Pythonic string manipulation. Right? So this is basic Pythonic string manipulation. So that will. So what this does, if you don't understand, is that you take the second half of parent 1 from the cut from this location onwards, and the first half of parent 2. Right? And now you return the child. Well, you should return the cut too. Right? Yeah, you should. I'll return the cut as well, so that we can display where exactly we are cutting the parent. Right? So we return the child and we return the point of the cut. Right? So I think this is fine. I think there isn't any mistake here. So okay, so what does this look like? So let's print this. Right. So let's create two random parents. P1, P2 is going to be what is the name of the function? Random individual? I think it's random individual, right? Yes, it is random individual. And this time I'm not going to forget to put the brackets. See, at least we don't have to write this dot everywhere. So that is better. But forgetting the brackets is kind of annoying. Right. So we have two parents, and let's find the child and the location and the cut, right? So we are returning the child and the cut. So the child and the cut is crossover between P1 and P2. Right. So let's print all of them. Let's print no f strings. So parent 1 is P1, yeah, P1R, and then we do parent 2, the cut point and the child. Okay, so this is going to be parent 2, the cut point is at an index of cut. That's what we call it. Yes. And then the child is child R, and okay, and let's display the cut, right? So which is equal to uh, uh, parent 1 at point plus. So how do I show this? So it should be parent 1 and cut let's delete all of this. It's getting confusing. Cut. In brackets. Plus int to cut bracket quote. And then cut square bracket, then bracket again, and then quotations, then bracket again. Okay. Okay, so here you can see that we cut off at index 13, at the 13th position. So KRCW, this part is the same as here. So KRCW, FUR, TKZ. So this is same as this. Right, so this is the same as this. Then the next part comes from here, this and this. So this is working, right? We have created a valid crossover operator. So a crossover function is working. And let's very quickly do mutation, because I see that we're running out of time. So let's do mutation. Let's call it mutate, not mutation. So you give it some odd of like some chance of some every single portion being mutated. Right? So individual, and let's say the mutation, the odds of getting mutated is 5%, right? So it's 0.05. Let's say that's the odds of getting mutated. So the characters that can be mutated are, let's take all the characters in individual. So for I in range length of pairs, if random dot, so we take a random value. If this random value is less than the mutation rate, which is 5% here, then what you do is there's a scars or cars. Cars I equals random dot choice from genes. And that's it. So you return, so you combine characters, all the characters into one string, and you return them. So you return dot join. Okay, this should be, I mean, this is very simple. I've done this a million different times. There shouldn't be anything wrong here. So let's check. So you create a new random individual. And so individual. So print print before mutation. And okay. So before mutation, the value before mutation, and then let's mutate it for different percentages, right? So we took 5% mutation over there. So let's do 5% mutation. Let's do 2% mutation, and let's do 5% mutation, right? Sorry, 5%, 20%, 50%. So for rate in 0.05, what is 20%? 20% would be 0.2. And even higher, so like 0.5. Let's try all of them. And let's see what it looks like. So mutated values, mutated individual, just mutated. Mutate this individual with mutation rate equals the rate. So and then print it. So printf for post mutation with the rate. Say, then let's mutate it, right? That's what I call it. Okay, I think that's it. Oops. Mutate. My bad. Okay, so this was the mutated, this was the original string, and then you can see this mutated string has changed a lot. Right? Like the difference between this and this was very low, but the difference between this and this is very high. Like more than half of the values have changed. Right. So we have, and so that's it, right? We have done everything. Right. So now let's combine all of these things together into a full generation. Right. So you create generation. So like everything is done. So uh, uh, new generation, next generation, static PNG. So let's call it next generation. So what do you need? You need a population, you need a mutation rate, and you need survivors. So first things first is your new population is an empty list at the start. Then you want the survivors, right? So the survivors are the individuals that are not going to change, who are really, really good, right? So so to find the survivors, what we need to do is we need to take the whole population of solutions, and then we need to sort them, and then and then we need to add them to the new population, right? So okay, so let's create the sorted population first, right? So sorry, I'm going a little quickly because we're running out of time. My my throat is dying, so I'm sorry if I'm going a little fast. And if you're having trouble following along, uh, email me or join me during office hours, and I'll help you out. So let's sort out by let's sort the population by the key of the what is the name of our fitness function? Fitness. And uh, oh my God, there's another requirement for the sorted function that I don't remember at the. Oh, reverse. Yes, so it can be reversed. Yeah. And then we take the sorted population and we add it to the new population, right? So and how many do we add? We add this many. So we take this many survivors and we add it to the new population. Like the elite. These are like the best. So the new population gets extended. Is it extended? No, it's just extended. So sorted underscore pop, you take survivors, right? And that's it. Okay. And now we do the now we compare now we do the parent selection process, right? So while the length of the bracket is so while the length of the new population is less than the length of the supplied population, you keep doing this, right? You keep creating. So you have parents do uh, tournament selection on the population, and there was a factor of 3, right? Tournaments. Yeah, three is fine. Let's leave it at 3. Let's not mess around anymore, right? So your parent 1 is doing tournament selection on the population. Let's do parent 2 as well. Sorry, the same thing. Then the child and the cut. Well, the cut is no longer needed, but whatever. It's a wasted variable. Yeah. we won't do anything with it. So is crossover between parent one and parent two. You mutate. Well, do we mutate the child or do we mutate another individual? Let's not mess around with things. Let's just mutate the child. But generally speaking, you can take another individual from the population and mutate that. But in this case, let's just mutate the child itself, right? By a mutation rate. Right. Okay. And then you take this child and then you add it to the new population. This time it's not extend, it's append. Right. I think I did everything, so let's return the new population. Okay. I think this is doing everything. Right. Let's test it out as usual. So let's create a new population. We'll finish in the next 3 minutes. Let's create a new population of 10 individuals, or I don't know, 20 individuals. Print Gen 0. I don't know why I typed out 0 instead of writing 0. I in top. What? Oh, I in top. Okay. Print f string independent. No, not independent. I R 21 fitness equals fitness of I. Okay. And then we do the same thing again. So we do pop. We already used new pop somewhere, right? Let's do pop 2 is next generation on the old population. And let's do this again. Instead of Gen Z, it's going to be Zen 1. So I in pop 2, I article 15. Yeah, let's see. Fitness is here. Oh, it requires mutation rate, and I thought I made them optional. Oh, let's do mutation rate is 0. Oops, 0.05. I didn't give them a value, and so survivors is, I don't know. Let's so start with one survivor. Right. So let's do this. Okay, and then let's do this. Oh, pop underscore 2. Okay, and already you can see that Gen 0 had much lower average. No, there are no ones. There are no zeros in Gen 1, but there are lots of ones. Like, so in the original, there were lots of zeros in Gen 1. Here, there's already not enough zeros. Right. So finally, let's do this. Let's do this very quickly. Let's create a full run, right? So run genetic algorithm. So we have all of them, right? So let's say uh, pop size of, I don't know, 200. Mutation rate of 0.05. Mutation rate of 0.05. The threshold for early stopping max generation is 500. What else is needed? Nothing else is needed. That's it. So let's start off. Population is equal to create underscore population of pop underscore size. We need to know what's going on. So history variable is good. Then for generation in range max generations, because we're going to stop at that max generations. The current best is the max of the population, comma, with the key of the fitness function that we have created. Best, so that is the best fitness. So the actual value of the best fitness, because we needed to compare, is fitness of the best. And let's constantly append it to the history so that we know how we are improving over the generations. So append to the history to the list of history is generation best underscore fit. Okay. Oh, wrong brackets. My bad. Okay, so if we do this like 10 times, but let's just print them out. So if generation modulo 10 is equal to 0, so every 10 generations we just print out the history. So f generation s3 best is best, and fitness is best underscore fit. That's what we call it, right? Yeah. Best underscore fit slash len of the target. Okay. And then if the we stop, so what is the point of stopping, right? So if the best fit is uh, is equal to, so if the best fit is 21, then that means we have hit the target, right? So that is one way to know if we have hit the target, right? So print target reached, generation colon best submission marker. Right. I think that's it. And if we hit this, then we break out, right? And then okay, what's going on here? I think this is all correct. So and we haven't done the actual next generation. So the population is next underscore generation with population, comma, the supplied mutation. Right. And then what you do is for the function, we're still in the function, so you return history. All right, and that should be that. Let's see if there's any major error. And finally, let's run it once. So the target, we already know the target. So let's run. What did we call it? Run genetic algorithm. Oh no.
I think that's
yeah, spelling mistake for generation in max generations. Let's do this. Okay, what did we call it for generation in range? Oh, it's max generation, not next generations. Okay. Sorry. Oh no. Generation is not defined. Oops. Generation. Let's do this here. And we reach the target in generation 42, which is another very good number, right? And you can see that over the generations, after 10 generations, we created this, which has a fitness of 3. And then we rapidly increased from 13 to 18, but we plateaued between generation 30 and 40. The fitness didn't improve at all. Eventually, at generation 42, we peaked. Right? And I will create you. It's very easy to create like a matplotlib visualization, but you can see that we managed to hit the target, and you can see like, okay, this is what it looked like step by step. And here you can see that like how we are getting closer and closer to University of. Eventually, we hit University of Leeds. So this is a very good example of like how this model is learning, right? How you're slowly going from something that is completely meaningless to the fitness is improving, 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 and eventually you're hitting University of Houston. Okay, we went over our dedicated time by a lot, so thank you for staying in. Uh, uh, Yeah, all right. So I'll share this code with you. I'll post this. Like this is not very good code. This is kind of terribly written with all sorts of bad practices, but this does. So tomorrow we are going to start something else. Thank you for joining in. Uh, I will share the code later. I will share the code right now on the Teams channel. And I guess my throat hurts. So I'll stay safe in all the rain and everything. I will see you all tomorrow at 4 o'clock. Thank you for hanging out.
Have a good one, Professor.
Thank you.
Thank you, Professor.
Recording. Thank you, everyone.